circuits for simulating Fibonacci.
Thank you very much, Nick, and Adrian for giving me the opportunity to present this work here today. So I'll be talking about minimal quantum circuits for simulating Fibonacci anyons, which is a topological phase of a topological order, basically, as I would describe. This is a work that has been done actually over 3 summers with 3 different students, Sarah Bizezo and Richard Allen. They were both undergraduates at the time. And Joel Kommernening was a graduate student in Germany that I borrowed for a summer. And Steve Simon is a collaborator. So and by way of, I guess, I should just maybe also mention this, that, I apologize if this talk is not quite polished. This is just the second time I'm giving this talk. So some references in particular need to be added. So I apologize for that. So by way of motivation, let me tell you a little bit about the idea of topological approaches to quantum errors, in that quantum computers, the main problem with building them is the existence of errors. And so basically, what are the approaches to these errors that is related to topology? So one approach that was pioneered by Kitaev in '97 was this idea of topological quantum computing, where the idea is that to store quantum information into what are known as topological degrees of freedom of certain states of matter, which are highly entangled. And these states of matter are actually quite robust, and therefore, if you basically manage to store quantum information into these states, then the quantum information is basically protected from the environment, and it's protected by the topology of the system. So you can think of this as the hardware approach, or a passive approach, passive in the sense that physics of the material basically takes care of error correction for us. Another approach, which is the idea of topological quantum error correcting codes, and which was also pioneered by Kitaev, but also the idea of, I guess in general, you can argue that quantum error correcting codes are all sort of somewhat use the same idea. And here the idea is to basically take the quantum information and spread it over the global state of many entangled states, many entangled qubits. And the approach in topological quantum error correcting code is that particular entangled state is the ground state topologically ordered model, basically. And so by effectively storing your quantum information into this highly entangled state, you are again protecting it from the environment. So you can think of this as maybe the software approach to quantum error correction, or the active approach, active in the sense that you have to actively build this entangled state and store your quantum information in that and do logical operations with it. So now let's talk about this second approach a bit more. So again, the key idea is to effectively simulate a topologically ordered state using generic qubits. And then this simulated state basically inherits the topological protection of the original model. That's sort of the basic idea of these codes. One very famous example of this approach is the Turing code, or the surface code more generally, where the underlying topological order is an Abelian phase. I'm sure that you've sort of heard a lot about this code. The main advantage of this code is the fact that it has very high error thresholds, and also the circuits for implementing this code are relatively simple. And also, all the Clifford gates can be done sort of exactly transversally. The cons mainly are the high overheads. If you want a very good sort of high, if you want very accurate gates, basically, you have to use many qubits, too many for any experimentalist who likes to sort of work with them, usually. And also, non-Clifford gates, such as the T gate, are very expensive to build in this approach. So the other approach, which is more relevant to what I will be talking about, is the idea of building your quantum error correcting code based on what are known as non-Abelian topological phases. For example, the double Fibonacci model, which I will be explaining soon. Here, I just basically flash this out, that some pros and cons of this approach. I will talk about non-Abelian models in a minute. The advantage of this code is that this code also has high error threshold, at least for a memory that has been studied. And also, all the gates can be done purely topological. And the cons is that basically includes the fact that the circuits for implementing the code are actually much more complicated than the toric code. And also, both common gates are approximate. So we always have, so we don't have the advantage of having Clifford gates exactly in this code. Everything has to be approximation. And so that adds to the overhead, depending on the calculation that we want to do.
So what is the transversal gate set for the non-Abelian?
There is none.
Yeah.
Unless you want to just do your actual braid operations. Those are exact, but everything else you have to sort of build out of them.
So if I wanted to think about the analog of magic state distillation for non-Abelian codes, like what are the states that I'm trying to use?
Yeah, so you don't, well, I mean, the approach is a little bit different in a sense that, there's no difference between like an H gate and a T gate in this approach. Everything has to be an approximation. You have to, depending on what accuracy you want, you just have to have longer and longer braids, basically. That's yeah. Okay, so let me, again, I'm sure you're familiar with the idea of anyons, but just for completeness, I'll just briefly go through this. As you know, anyons are basically identical particles in two space dimensions. Why do we call them anyons? Imagine you have a two-dimensional space and you have time in the third dimension. If you move these particles around each other, their world lines trace out braids, and there's a difference between exchanging these particles clockwise and counterclockwise. You actually get completely different braids that are not equal to each other. So if I show these two braid operations, the clockwise exchange and counterclockwise exchange, they correspond to the two different operators, which are not equal. Therefore, so since sigma is not equal to sigma inverse, sigma squared is not equal to identity. So if I basically exchange two particles twice, I don't get back to where I was. Therefore, the options for sigma are not just +1 or -1, which correspond to bosons and fermions. They could be generally phases, any phases, which are called abelian anyons, or in more complicated cases where this operation is actually a matrix, then the corresponding identical particles are non-abelian anyons. So that's basically a one-page reminder of what anyons are. So now let me just basically get into Fibonacci anyons, which is a particular type of non-Abelian anyons. So again, these are identical particles in two space dimensions. They carry a quantum number, which we call topological charge. I think it is called different things in different literature, but for the purposes of this talk, I would call it topological charge. This is a notation I'll be using in this talk for this. This dot is basically topological charge of tau. So the theory basically has two sectors, one or tau, one is vacuum, and tau is a non-trivial topological charge. And there are rules for combining this topological charge, similar to the rules that exist for combining spin. The rule in this case is that if you combine two Fibonacci anyons, they either annihilate each other and you get vacuum back, or they result in a single Fibonacci anyon. They do this with different probabilities. So again, this is a notation that I'll be using. If I encircle like two anyons with a circle and write a number next to it, it just corresponds to the fusion result, to the result that comes from potentially fusing what is the content of this oval. So anyway, so if you have two anyons, that basically corresponds to, you have sort of two choices for fusing these, and this fusion space actually is a Hilbert space. So for two anyons in general, you have a two-dimensional Hilbert space. If you keep adding your anyons to your system, so if you have two, the Hilbert space is two-dimensional. If you have three, and you can see that there are three different ways to fuse these three to each other. So the corresponding Hilbert space is three-dimensional. And you can do, if you can try it with four, and you see that it's going to be five-dimensional. And so in general, if you keep adding them, you see that the dimensionality of the Hilbert space grows as Fibonacci numbers, hence the name. And so because the rate of change of Fibonacci numbers in asymptotically is the golden ratio, basically this rate of change of Hilbert space is also called quantum dimension. So we say the quantum dimension of Fibonacci anyons is the golden ratio. So it's an irrational number as opposed to, say, 2, which is the quantum dimension for just a regular spin 1/2, for example. Okay. All right. So one other, I guess, detail I have to sort of explain, and that is the order of fusion can actually be used as a way to define a basis for the Hilbert space. So, for example, in this case, if I have 3 anyons, if I choose to first fuse the first 2 and then add the third one, that defines one basis. But alternatively, if I choose to first fuse the second 2 and then add the first one, that defines a different basis. And these two different bases are basically related to each other with a unitary operator, like any basis change. And in this case, this unitary operator is known as the F operator or F matrix. F comes from fusion, I think. So again, I just want to explain in notation. So here I'm just showing you the anyons, but now imagine if I show you the word lines of these anyons. Here, time is actually flowing from top to bottom. So for each of these red dots, I have a tau particle, and they, in space, they sort of when I fuse them with each other, their word lines basically meet in space time. So they basically fuse into M, and then this M is fused with tau, and I get a tau back, which is the overall charge of this triplet of anyons. Or alternatively, I can just fuse these two first, the ones on the right, that the total charge, say M prime, and then combine M prime with the first one, and that gives you basically another way to get to the total charge of tau. Now, if I basically slightly modify this diagram by pushing this head on the left part to the left, and then this right part to the right, I get this notation. So this is just basically a deformed version of this second line. And this is actually the notation that is mainly used in the literature of string net model, which I will be talking about later, or in general in tensor categories. So I guess I just wanted to sort of make this connection that how this diagram is actually related to the idea of change of basis. But this is what we will be using. In the case of Fibonacci anyons, it just happens that this sort of F operator has this matrix form. Okay, again, very quickly, Fibonacci anyons are best known in the quantum computing literature because they're known to be universal for quantum computing. So that property comes from the specific operators that correspond to exchanging Fibonacci anyons, or the braid matrices. So if we basically exchange 2 anyons, this operation can be represented by this R matrix. Again, this is the sort of the word line version of that. Now you can imagine time is moving from bottom to top. So if I just create a pair of particles out of M, and if I exchange them, then they're related to each other by this matrix, and this matrix has this form. The fact that it's diagonal means that if I exchange 2 particles, their overall charge doesn't change. So if I have 2 tau anyons, and if I exchange them, and if the total charge is 1, or vacuum, I get the first phase, and if the total charge is tau, I get the second phase. And if any of those I or j is just identity, then R is basically trivial, it's just 1. Okay, and then another thing which I basically talk about this in the paper. I don't think I'll have time to talk about this in this talk, but just another property of these Fibonacci anyons, which is related to the braiding operation, is the idea of twisting. And that basically means that if you take one of these anyons, a single one, and just twist it around itself by 2 pi, then there's an operator corresponding to that, and that operator is basically a phase, which is again related to the sort of the braiding matrix. Okay. All right. So these are basically a quick introduction to Fibonacci anyons. Now we want to basically come up with a model to realize this with just real qubits. We want to see how we can actually sort of simulate this model with real qubits. Unfortunately, there is not a sort of a mathematical model out there, a spin model that actually creates just a Fibonacci model for you. But there is a model that actually creates what is known as a double Fibonacci, which is basically 2 copies of the Fibonacci model. So you can think about it as basically 2 layers of Fibonacci anyons. You have one layer, which we call, say, right-handed anyons, which has the braid matrix and the twist phase that I just showed you. And then there's another copy, which I call them left-handed anyons. And these basically have the opposite phase if you braid them. If you sort of braid, say, the two tau anyons in the top layer, or say if you twist one of them, you get phase of e to the I for 4i pi, over 5. Whereas for the bottom one, you just get a negative version of that. So these are basically have opposite chiralities. So this model, fib cross fib bar, basically its spectrum consists of 4 sectors that just comes from combining a 1 and tau and 1 and tau bar. So you have these four options: 1, 1, 1 tau, tau, 1, and tau, tau. Now, how do we actually sort of?
So they always leave like sort of bound states like that?
No, they're not bound. I mean, I guess. Well, yeah. I mean, I guess you can also sort of think about it as bound, but it's basically all the 4 options. However, there are 4 ways that you can actually sort of combine them. Right. So that's what it is. So in other words, if you have a 1 tau, it just basically stays a 1 tau throughout their combination. It doesn't switch into some other. In that sense, I guess they're bound. Okay, so how do we actually sort of realize this double Fibonacci model? So Levin-Wen came up with a model to actually sort of realize this with a sort of a spin Hamiltonian. So let me just very briefly again tell you just the essential things about this model. So the model is actually defined on a trivalent lattice, and it consists of strings. So strings that actually, so you can just imagine you have this lattice, and then you have strings or ribbons that can actually be superimposed on this lattice, or usually they basically sit on the edges of this lattice. So these string types have basically 2 types, 1 and tau. That basically reminds us of the Fibonacci model. And then there is basically additional data about the model, and that is if you basically have a closed loop and a contractible closed loop, what is the sort of the weight corresponding to that? And it just happens that for a sort of a tau string, this loop has the weight of golden ratio or phi. For the empty string or 1, a loop is just basically trivial. And then the rules for they're branching rules basically, and that means if we come, say, if on this lattice, if we, like wherever 3 edges come together, what rules of like how should these strings behave? And then finally, there are rules for local change of basis, or these F operators that I talked about. That you can imagine that, like for example, if you have a shape like this. Here, you can actually, in principle, you can just do a local change of basis and convert it into like this kind of shape. So the value of this F matrix is also sort of part of the data that you have to have for this model. And then there are also additional consistency rules concerning this F and D values, which I will not get into, but it's just for completeness, it is there. So now let's look at this model a bit more carefully. So this, actually I should say, the space of these strings and with these branching rules actually defines a Hilbert space. And so you can define a Hamiltonian in this Hilbert space. And so they define it. So Levin-Wen basically defined this Hamiltonian, which is very similar to the Tori code Hamiltonian, as you probably recognize. It consists of 2 terms. The first term is the vertex operator, which basically governs the branching rule, or enforces the branching rule. It acts on 3 spins meeting at a vertex, and it basically in this Hamiltonian it sort of favors a particular combination of strings. So in like and in the case of this double Fibonacci, these branching rules are actually basically coming directly from the rules for combining Fibonacci anyons. So all the rules are, so for example, 3 empty strings can meet because that corresponds to combining 2 empty string, 2 ones with each other. A triplet is also allowed because that corresponds to tau cross tau, giving me a tau. And also two sort of taus coming together is also allowed because that corresponds to either tau and tau giving me identity or tau and 1 giving me tau. So for all of these guys, QB is satisfied. And when we say QB is satisfied, this basically means that these states are the +1 eigenvalue, a +1 eigenvector of the QB operator. When QB is violated is when a single tau line comes to a vertex. So in other words, when QB is enforced, all the configurations that we can have are basically in the form of loops or nets like this. So you can again see this is similar to the Tori code, but in the Tori code you only have the loop configurations, but in this case you also have net configurations because this kind of branching rule is allowed. And then this sort of violation rule basically tells you that, again, similar to the Tori code, you can't have empty strings or open strings. Open strings are basically disadvantaged in this model, and they correspond to excitations. So when QB is satisfied, we are basically in a subspace, which we call it stringnet subspace. Now, to get to the ground state of this Hamiltonian, we also have to satisfy the second operator, BP, which is a plaquette operator that acts on 12 qubits, like this. And the fact that this operator is actually acts on 12 qubits is one of the reasons that experimentalists are very hesitant to try to engineer this model in the lab, because it's very hard to create a 12-body interaction like that. But anyway, the effect of this. So what this BP operator effectively does is that in this subspace of strings, stringnets, and loops, BP basically picks up sort of a particular configuration just from all the possibilities of different sort of loops and nets. BP operator basically selects a particular sort of superposition of these nets, and you can sort of, I guess, to understand this, you can think of the effect of BP as basically an operator that adds a particular type of string to each plaquette. And this string, which is called vacuum loop, not to be confused with the sort of vacuum state of empty strings, this vacuum loop is basically this particular superposition of an empty loop and a tau loop, basically. And I should also sort of mention that when this notation, when I have this gray dot inside the plaquette, it basically means that there's like a hole inside each plaquette. I punched a hole inside each plaquette. So these loops cannot contract in the middle. They actually have to be absorbed into the edges. And there are rules to that. If you basically put a string on top of an edge, how to actually sort of absorb it into that edge. So that's basically what BP does.
What's B again?
Oh, sorry, this is just a normalization factor. It's square root of 1 plus 5 squared, yeah. In general, in our lattice, that's basically what BP does. We basically, to enforce BP, we just basically apply a BP to each of these plaquettes. And that after we absorb these sort of strings into the edges, the result is the particular superposition that corresponds to the ground state of the double Fibonacci model. So in this picture of looking at this DFib spectrum, the 1-1 corresponds to the ground state where both QB and BP are satisfied on every vertex and operator, on every vertex and plaquette. Another, I guess maybe I should just put it out here, another, I guess, term that I'll be using is that when I talk about topological charge, or charge for short, in these models, I basically refer to these different excitations. So in other words, the ground state has no charge, but I can have a charge of 1 tau or tau 1 or tau tau. These are basically 3 different flavors of excitations that I can have that I just refer to colloquially as charge. And say yes. I mean, these sort of 3 excitations basically correspond to various combinations of QB or BP or violation or both. So I guess one simple way to think about excitations is that when all your QBs are satisfied, but then BPs are not satisfied. So that corresponds to one type of excitation, just BP violation, and that's within the stringed space. In the original Levin-Wen model, the other excitations correspond to violations of basically these open strings when you have a string that actually ends at a vertex. But these excitations are actually a bit problematic to work with, partly because when QB is violated at any point, all the BP operators in the surrounding plaquettes are also ill-defined. So if we actually want to we actually want to actively create these excitations, we need to find a way to create them within the stringed space. And a trick, so it's a trick to do that is basically to come up with to modify this lattice, go to what is known as the extended Levin-Wen model, in which we add a tail to each plaquette. And when we do that, we can actually, if I just go back, you can see that if I have basically strings that are ending on vertices, if I add tails next to them, I can effectively sort of nudge this excitation into the tail like this. And when I do that, then I have basically gotten rid of my QB violations because a single tail is just sticking out without having anything coming to it. So whereas this bottom of the tail is a vertex, the end of it is not a vertex. So I can actually have a single thing coming out. So I can actually create my excitations at these sort of open tails without while staying within the stringed space. Okay, so now let's just see what happens actually. What is how do we basically analyze these, or rather, what is exactly the connection between these sort of open strings ending in tails and the spectrum of the double Fibonacci that I talked about. So let's just look at one of these plaquettes. When we have a tail or a string that basically sits on a tail, there are actually sort of several options of how to superimpose the string on this vacuum loop. We can, as I'm showing it in this example, I can just bring the tail on top of the string, the loop, or I can also have the option to bring this string underneath the lattice. Or I can actually also have the option to bring 2 strings over and under the lattice. They can actually meet. So it turns out that if I basically, I mean, so when you have 2 strings sort of cross each other, there are rules for actually resolving it, or that means getting rid of crossings and then just converting into just vertices and strings meeting each other. It turns out that this configuration, basically a combination of a vacuum loop and a string going over the vacuum loop, corresponds to the tau 1 excitation. And when the string goes under the lattice, it corresponds to a 1 tau excitation. And when you have both strings, then this is a tau tau excitation. And this should be compared to the case where I create the vacuum state or the ground state or the 1-1 state, which corresponds to applying a BP to a single plaquette and just adding a vacuum loop to that plaquette. So 1-1 is basically the same thing as BP, but now in this model, I have three other operators that are similar to BP, which are the combinations of the vacuum loop and these strings. I mean, this is again another detail, but unfortunately, it actually shows up in the results, so I have to just briefly mention it. So these strings, these tau strings that come in the tau tau, when they meet each other on each side, it's just basically bringing 2 taus together. There are 2 ways to combine them. They can either just combine into an identity or another tau. So and it happens on both ends of the strings. So if on both sides they fuse into one, you just get a loop. If basically only one of them is 1 and then the other one is tau, you get these two in the middle. And if both of them, you get 2 taus on the two sides, then this is just the last one. And so these 4 in the bottom line are just 4 components of the tau-tau excitation. They all have the same charge, but the different combinations can show up depending on what kind of lattice you have. All right. Okay, so now let's just talk about how we can actually sort of simulate this model on a system of qubits. So we actually can imagine our qubits sitting on the edges of this hexagonal lattice with tails. And this, we can sort of encode the 1 and tau string types to qubit states 0 and 1. It's going to be guessed. And there is one sort of nice simplification when we actually think about small lattices. So first of all, we have, we assume spherical boundary conditions. So that means for all these sort of plaquettes that I have on this side, you can imagine there's like one big plaquette on the other side of the sphere to just complete this. So when I sort of focus on a single plaquette like this, you can just think of this as one hemisphere, and then where the other hemisphere is on the other side of it. So there's a P1 facing us and a P2 on the back of the screen. Also, all these sort of edges are actually connected to each other without any sort of strings coming out of it. So in other words, all these qubits are have the same state. That basically means that we can replace them with just one qubit. So in other words, a sort of the simplest possible lattice with just 2 plaquettes on the 2 sides of the sphere can actually be realized with just one qubit acting as an edge between two hemispheres. But there's not much that you can actually do with just this simplest case. The next interesting case is when you have 2 plaquettes. So 2 plaquettes facing us and one plaquette on the back. In this case, again, you can argue that all these plaquettes on the edges, all these qubits on the edges are basically are in the same state and also on the left side. So I can replace this with this sort of tilted theta shape, where I have 2 plaquettes, P1 and P2 facing us and P3 on the other side. So in this case, I'm basically representing 3 plaquettes on the 3 qubits. And as we'll show, you can actually sort of see fusion of Fibonacci anyons just with these 3 qubits in this sort of smallest model. To look into properties related to twisting and braiding, we should actually go to a case that we can actually create these chiral excitations like tau1 and 1 tau, and for that we have to go to the tailed lattice. But again, here we can play the same game and say, if I have a single tailed plaquette, I can identify all the top ones with one qubit, and same for the bottom. And so with 4 qubits, I can realize 2 tailed plaquettes. And we can actually sort of show the twisting of a single anion in this model. And for actually showing braiding, I need at least 3 plaquettes. And that can be done with 9 qubits and this sort of tailed version of the theta lattice. Okay, so these are basically the smallest lattices I'll be working with, and that's sort of the trick that just this identification of boundary conditions just allows me to use these sort of very small lattices. All right, so the properties I want to show are basically fusion and braiding. Specifically, sort of the first. In this, I guess, version of fusion, I create 2 pairs of tau anyons out of vacuum. That's the, this figure on the left. And then I change my basis. I go to a basis in which I look at the fusion channels of the middle 2. In other words, you can imagine there's basically word lines coming out from the other side, and then I fuse these things, and then what comes out of that. And it turns out that again, for these 2 tau anyons, the charges that I can get are either 1 or tau, which I'm showing here and here. And it turns out that the corresponding coefficients are 1 over phi and 1 over root phi. So we basically want to reveal these particular coefficients, which are the signature of fusion of Fibonacci anyons. And then for the braiding, again, we start from the same place as before with this state, and then we just exchange the middle two anyons and look at the and then just change the basis and then look at the coefficients of these coefficients of the two terms in this basis. And it turns out that you basically get these extra braiding phases in addition to the fusion channels that we see in the first case. So these are the two sort of experiments that I am hoping to explain the remaining time. All right, so I need to sort of explain another, I guess maybe sort of technical point, and that is this F operator, the change of F basis operator F that I talked about. In the context of the lattice, it can actually be used to sort of locally modify our lattice. So let's just see what happens if you just apply this to one qubit. So this is just to one plaquette. So I have a plaquette with sort of 6 states, and let's say I identify these 5 edges, and I apply an F matrix here, and I end up with this shape. Instead of a hexagon, I have a pentagon. Now there is this, I'm omitting the reference here, but this is a work from early 2000s, I think, from Robert Kunish and others, that they basically showed that this interesting property that the change of basis operator and the plaquette charge operator F and B actually commute with each other in the following sense. That if I basically apply a BP, or rather if I sort of measure the chart, if I apply an if I apply a BP operator here and I sort of measure the charge content of this plaquette, and then I apply an F to end up here, the result is the same as first applying the F, going into this smaller plaquette and then measuring the charge. In other words, if we actually apply these F operators to sort of change the size of the plaquette, the charge content of the plaquette does not change. That's sort of the basic sort of message here. And this is something that we'll be using in the following sense. So a single plaquette, well, maybe I should have said this, that it's hard to implement the BP operators directly because BP is actually a projective operator. I don't directly have a unitary operator that corresponds to that we can actually apply. So we have to come up with tricks to apply it. And this is in a sense a trick for applying the BP operator. So BP is just effectively sort of applies this entangling gate to all these qubits, but I don't know how to do that, but I know how to apply these F operators because Fs are unitary, so I can actually write a circuit corresponding to that. So I can actually sort of keep applying this F until I end up with just a single tadpole. I basically have all the charge content of one plaquette into one qubit with a tail and some extra legs like this. And now I know how to actually initialize a single qubit. And then if I do that, then I can just reverse the process and go back to sort of the entangled state that corresponds to the initializing a plaquette into the ground state, for example. So here, I guess here's another sort of example of that. I start with just an empty tadpole. I apply a single qubit gate to this tadpole, and that gives me sort of a particular superposition, which corresponds to the ground state. And then I apply a bunch of Fs, and I end up with this, the plaquette that has the sort of the right sort of superposition of identity and tau strings. So I can use this process basically for initialization and measurement. So the thing that I described in this direction is the initialization, but I can also, if I'm given a plaquette and I want to understand what is the charge content of that, I can actually reverse this process, go back to the tadpole, and then measure that single qubit, which is the tadpole, and that will tell me if what the charge content of the original plaquette was. So this is a very useful trick. So in general, every plaquette can actually be converted into a tadpole. Then I have these tailed plaquettes then I have this generalized tadpole. Then instead of just one tail, I also have like an inward tail inside the head of the tadpole. So it turns out that so for each of these sort of these operators, the BP or 1, 1, or all these other operators which correspond to the other excitations of the DFB spectrum, I can actually find a tadpole sort of version corresponding to that, which basically gives me the recipe on how to create that kind of excitation inside a particular planet. And if you basically sort of work this out, there's this whole list of how these these different operators look like. So again, any of these kind of excitations that I want to create, I can just start with a tadpole, then open up the tadpole, and then in the lattice spaces, I end up having that particular excitation. All right. So now let's just go back to the sort of the fusion. This is the, again, I'm just repeating this. This is the relation. Sure.
This procedure that you described,
Yeah.
I can understand that it works, but it's much less clear to me if it's efficient.
Yeah, I mean, I guess you have to think about like what are the alternatives.
Yeah, I guess I'm asking like, is there an argument that this is efficient using this setup?
Well, I mean, so for ground state, for creation of ground state, so this is actually, so efficient in the sense that you mean in the largest scale.
Efficient in the sense that like I can implement it with a circuit with relatively shallow circuit depth.
Yeah, I mean, I actually really don't know of any other way to do this at this point. I mean, for larger scale implementation of the ground state, I know of alternative ways for doing the ground state, but they have the same scaling as this one. They're both square root of L.
I guess I'm just asking because it doesn't seem like this algorithm that you described is very parallel at all. It seems like very sequential.
This part of it is very sequential, yes. Yeah.
There's no strategy to parallelize it.
Well, not the F part of it. I mean, that part, I guess, necessarily has to be in parallel because you want to go from one to the other one. But as I will show you, the circuit is really, the end circuit is so simple that
the computation order, you have to compute it.
yeah, you have to be one after each other. So that part is hard to sort of parallelize. Yeah. I mean, the circuit implementation of that F might be combined, and you can maybe save a few gates there. But the actual sort of the sequence of Fs, yeah, it has to be sequential. All right. So again, this is a fusion rule that I want to do. So I basically want to create two pairs of excitations, and then change the basis, and then look at the total charge of, say, one from each pair. So I can actually realize this in just a Tato lattice with 3 qubits. And so here the idea again is that I create a pair of excitations. So if this is Placket 1 and Placket 2, I create a pair of excitations between P2 and P3. That's this one. And then another one between P1 and P3, and that's this one. And then I look at the total charge of P1 and P2, which has to be the same thing as charge of P3 because this has spherical boundary conditions. And so the excitation I can use in this case, so remember this is a lattice without tails. So I can't have any QB violations in this case, but I can just create it with Placket operator violations. And the excitation that corresponds to that just BP violation is this particular component of the tau-tau excitation, which we call tau-tau 1-1. And as you can see, has this form, just has the vacuum loop and then 2 lines going over and under that corresponds to tau-tau, and then there are no tails, and that corresponds to this 1-1 subscript. All right, so this is basically again pictorially how it should look like. This is again, this is sort of a tau-tau excitation that I have, say, between P1 and P3. And I guess I should just point this out that when I put a vacuum ring in like n-1 plaquettes, because it has a spherical boundary condition, the nth plaquette actually has a sort of a vacuum loop too. So you can imagine there's a vacuum loop around the third plaquette too. So anyway, this ring is actually creating a pair position between P1 and P3, and then this ring is creating it between P2 and P3. And you know, if you're familiar with just how to combine rings, you can actually see that you can sort of, if you apply an F operator between these two rings, the result is actually, you know, this shape, just a ring between the P1 and P2 and a ring which has this sort of extra tail coming out of it. And but anyway, the sort of the point is that this corresponds to the 1-1 channel for the P1 plus P2, and then this one corresponds to the tau channel for the total charge. So to do this, we basically to initialize again, we start with this sort of tadpole basis with the trivial lattice. These two lattices are actually the same, so I can just imagine that I start from here. Then I initialize each of the heads of the tadpoles with just single qubit gates, which effectively creates this kind of excitation here. And then I apply an F operator to the middle edge, and that gives me this lattice basis back. So that corresponds to sort of creating these two pairs of excitations already. And now to go to this basis, to actually read the charge of P1 plus P2, we have to make another change of basis where we sort of come up with a way to sort of enclose the full charge of P1 and P2 into sort of the head of one tadpole. So you can imagine there is now one tadpole corresponding to P1, and then there's, you know, the sort of the inward tail of another tadpole is connected to a bigger head, which corresponds to P1 plus P2 or equivalently P3. So if we basically make this change of basis and measure this charge, the charge around this guy, that corresponds to the total charge of P1 and P2. So, and if we do that, we basically end up with this shape. Again, so you can see that, as I said, you know, the total charge that we're looking for is sitting on the edge of this thing. So here I have only a sort of a vacuum loop. That's what I, and but here I have basically the sort of a tau 1-1 and another component of the tau family. So if I actually write it down, it looks like this. This is in the basis of the inner tadpole, that's the first cat, and the outer tadpole, which is the second cat. So the first term corresponds to the outer tadpole having a 1-1, that's it. And then the second term is actually a combination of two ways of combining two different components of tau 1-1, tau. So tau 1-1 for both the inner one and the outer one in the first term, and then tau 1 tau and tau 1 for the second term. But this is just a detail. I mean, I guess I just wanted to sort of write it this way to just show you, you know, what is this that actually corresponds to this. But the bottom line is that for both terms, the middle one always has a charge of tau 1, but the total charge of P1 and P2 can be either 1 or tau. That corresponds to this one and these two terms. So, and as you can see, the overall coefficients actually match what we were looking for the two fusion channels of two Fibonacci anyons. So this is a picture of the actual circuit. Here I have my 3 qubits for the 3 edges. These single qubit gates are just basically initialize each of the heads. The F matrices are also relatively simple. The first F, which takes me to the lattice basis, and the second F takes me to this measurement basis. And so this state basically is the same as this. You can actually sort of see that. But this state is still a bit hard to read directly. So we apply these a few sort of extra gates to simplify this state and effectively push all the information on the fusion channels into a single qubit. So this is the state that we get at this point. So in principle, we can actually carry out the statistical measurement at this stage and just measure qubit 1 and just see if we can see peaks on 1/phi and 1/√phi. Or the way I guess I propose to do it is to just have this state pass through a filter, which actually maps this state into a 0, and then measure that state, which is this one here. So in fact, I mean, if you measure a 0 at this point, it just means that you had the right fusion channels in the beginning. I have this, I mean, maybe this is a sort of additional difficulty, but to add a work for other reasons, I didn't want to measure directly my qubits. So I added an ancilla qubit and had this sort of computational qubit to be a control into this control node, and I measure my ancilla qubit. So if the ancilla basically remains unchanged, it means that I had the right fusion channels. If it sort of flips, it means that I had the wrong fusion channel. So this is a circuit. Yeah. All right. So the next, I guess, item is braiding, which I just tried to go through very quickly. So this is again the relation that I want to check. I create excitations the same way as before, but now I switch the middle two and then make a measurement, go to the basis to make measurement. So for this one, I actually have to use these chiral excitations. So I go to the tail lattice. And the idea again is that I create my excitations in this initialization basis, but I have two tadpoles. Then I go to the lattice basis, I carry out my braiding there, and then I go to the measurement basis to sort of read the corresponding coefficients. I guess visually, this is how it looks like in the initialization basis. I have these, my vacuum loops, and then the strings, the tau strings coming over these, the vacuum loops. And I have basically circuits for actually sort of carrying out this initialization. Then I go I apply an F matrix, or several F matrix in this case, to go to the lattice basis. Then I carry out my braiding. So I end up with this configuration, and I guess maybe sort of you can see that these from going from this configuration to this configuration, I actually have exchange blue and red counterclockwise. And you can actually do this again with a combination of F moves, F operators. So this is braiding in the lattice basis, and then I finally go to the measurement basis to sort of carry out to be able to sort of see the phases. Yeah, I mean, this might be, so this is basically, I guess, maybe sort of breakout of how the braiding is done. Just with a sort of a bunch of F moves, we sort of move different excitations, and then we end up with, I'm just basically sort of flipping this last one to just have the same orientation as this, and you can see that the two pockets are actually sort of exchanged with each other with just 3 Fs. So this is the final result in the initialization basis, and again, I can actually write this result as a combination of having total charge 1 on the third qubit, or in P1, P2, with the right coefficient and the right phase, and the total charge of sort of tau 1 on the outer placket, or P3 placket, for the second term with this coefficient. And then the charge of the middle placket always remains at tau 1. I mean, the sort of single P2 placket remains at tau 1. So yeah, and again, this corresponds to these two sort of channels, and this is just another way to write this. This is 1 for the outer one, and tau 1 for the outer one, and then the tau 1, the inner one, is always the tau 1. All right, and this is the corresponding circuit. This is actually a bit more complicated, but again, it involves a bunch of single qubit gates and 2 control gates for initialization, a bunch of F moves for change of basis and braiding, and again another change of basis, and then again this state is a bit complicated to read, so we just add additional simplification sort of gates to end up with the state in which we sort of send all the information about fusion channels and braiding phases into a single qubit, in this case the second qubit, So in this case, it actually, we can't really do any statistical measurement anymore to see the phases. So the filter way is the only way to do that, at least in this context. So I basically apply a single qubit gate that maps this state into 0. Or any other sort of state that I want. So if I basically get a 0 here, that corresponds to this particular superposition, which has all the information about the fusion channels and braiding phases. So that's it. I guess I'm right on time. To summarize, sorry, I should have put summary up on top. So I showed you minimal lattices and minimal circuits for showing the basic properties of sort of creating the spectrum of the double Fibonacci model and demonstrating its fusion and sort of braiding properties with just minimal number of qubits, 3 qubits in the case of fusions and 9 in the case of braiding. I didn't talk about twisting, but you can actually look up in the paper if you like. You can do it with 5 qubits. And also additional structure of fusion with sort of like, the next complicated lattice, which is tetrahedron, can also be looked at and studied. And that's also in the paper that I didn't discuss. But with that, thank you very much for your attention.
Any questions from the online audience?
So have you run your circuits through these like circuit optimizer things?
Well, no, I haven't. So the fusion circuit, I guess I was just saying, I had a student who checked it on IBM systems a couple of years ago, and even at the time, it was actually sort of pretty good signal. But the rest of them, no, I have not checked. But I mean, I guess kind of one of the selling points of this work is that you don't need specialized qubits or special designs for checking these properties. Anybody with qubits can actually potentially check them.
No, I was asking more about if you could make the circuits even more concise.
Oh, no, I have not. I have not done that. No.
It's pretty straightforward to do because there are these packages that you can just run your
potentially, yeah. I guess the sort of the simplest case.
It's not that complicated now, but you can make it even a little bit easier.
Right. I guess I was just going to go back here. When it's sort of hard to imagine that this can be any simpler than what it is, but in this case, maybe some of these. I'm not showing you the content of these Fs, but there's like little circuits corresponding to each of them. So in principle, it's possible to combine like all of these together into something simpler, I suppose. Yeah. Did it make sense, actually? I also want some feedback on presentation. Did it?
Yeah.
Yeah.
I think so. I think that my understanding of the motivation is that you wanted to show that some of these things that people say about topological quantum computing is actually simulable on relatively small quantum computing.
Yeah, I guess point of this work was to just see what are exactly, theoretically, what are the smallest lattices, and then what are the simplest implementations at the sort of the simulation level that you can actually do this. By the time that this work was finished, nobody else had done it yet, but since then, 2 other groups have also done similar things, so it's kind of lost its novelty.
So when you say, do you mean smallest or do you mean simplest? Because I could have
smallest lattices.
Yeah, so I guess I could imagine you could have a different lattice structure that's not as small, but maybe enjoys some sort of self-similarity or periodic structure, such that you could do something similar to this, even if it's not particularly small.
And it's a triband lattice?
Yeah.
Well, if you can actually get something simpler than 3 edges or 9, it's like 3 plus 3 with the tails, then I'd be curious to see that.
No, I'm not saying that these things could beat these things. I guess what I'm saying is maybe you can adapt the lessons you learn from these to approach lattices that aren't just necessarily the next biggest one, but rather some other parameter that controls another family of lattices.
But I guess I'm sort of curious, like what you have in mind, like how could it be like in what sense would it be simplest? Simpler, like I guess if you're not talking about the size.
Yeah. So if you have 3 plaquettes and you're trying to add a 4th plaquette, you have a number of different ways that you can do that. And some of those, based on my understanding of your statement, will require more or fewer qubits to handle.
That's right. I guess that's right. Yeah, you can put them in like a quasi 1D version, for example, versus like I guess that's right.
Yeah, I guess it would be interesting to me if there was some sort of like understanding of like when you have a plaquette sequence, classifying the move of placing the next plaquette in terms of how it increases the number of qubits you need as some sort of resource system.
Yeah, I mean, I have done that kind of things for, like I said, I mean, the quasi 1D version, and then again for sort of a smaller lattices, I compare them. But yeah, I mean, I guess it's when you go to like up to 5 plaquettes, I think it's the same thing. But if you have more of them, then you have more options. I think, right? Yeah. But again, I mean, I'm interested in this question at the larger scale, and in the larger scale, I mean, there's not really much of a, it doesn't really, I mean, I don't necessarily need the smallest lattice or the sort of the simpler lattice, but in this intermediate level, I guess that question becomes more important. Yeah.
Maybe it's just not a regime that's interesting.
No, I mean, depending on what you want to do, it could be. You're right. I mean, smallest is not necessarily the simplest. That's a good point.
Any other questions? If not, let's thank Layla again.